Okay, so I am going to be working through this assignment right here, which is 1.8 Exploration and Practice number 1. It's about sequences, and I will be using the textbook here to complete the following. So let's dig right in. I just got to get my annotation ready to go, which I'm going to do now. And the first question says, what is a sequence? So if we look on page 53, we can see that the big idea of this section is that sequences can be thought of as functions, but they have their own notation different from other functions. So that is really what we want to take away from this. Sequences are just a type of function, but they have different notation that we use. And then if we look in the first paragraph, it says specifically a sequence is defined as a function whose domain is the set of all positive integers. Okay, so basically what that means is that what you plug into a function, into a sequence rather, can only be 1, 2, 3, 4, 5, 6, etc. So basically the numbers that you count with, those are the domain of a sequence. Number 2, each item in a sequence is called a term of the sequence. So instead of saying an output, we say that it is a term of the sequence. Okay, so that's basically what we're defining here as a sequence. It's a function, so it's a type of function whose domain is only positive integers. Okay, so let's go ahead and scroll down here. It says read through the introduction to the activity on page 53. Okay, collection of dots below form the first 5 terms of a sequence of triangular arrays. The numbers of dots in each collection form a sequence of numbers. Okay, so here's a sequence of numbers. Step 1, complete the table to show the number of dots in each of the terms pictured. Okay, so let's see here. So this is term number 1, and there is 1 dot. This is term number 2, and there are 3 dots. This is term number 3, 1, 2, 3, 4, 5, 6. There are 6 dots. Then we have 6 plus 4 is 10 dots. Then we have 10 plus 1, 2, 3, 4, 5 is 15 dots. So we can recognize a pattern here. It says, notice that after the first term of the sequence, each subsequent term adds a predictable and increasing number of dots to the previous term. So here we added 2, then we added 3, then we added 4, then we added 5. So we might expect that the next one we would add 6, right? And if we, put these dots here, we can see that yes, you would add 6 to find the next term. So use this fact to complete the table for the next 4 terms. Okay, so let's clear this and let's scroll down. So here's the next 4 terms. So the 6th term, again, we would be adding on. And since we had, let's see, we had 10, we had 15. So this would be adding 6 to that. And that would give me 21. And then I would add 7, and I would get 28. And then, is that right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 15. Add 5. Yep. And then I would add 8, and I would get 36. And then I would add 9, and I would get 45. Step 3, this process can be continued for as long as you want. You can even think of it as going on forever. Oh, wow. Imagine that. Explain why the set of ordered pairs, term number, number of dots, describes a function. So we need to go back to our definition of a function, which is each input has exactly 1 output. So what I can say here is each term number has exactly 1 number of dots associated with it. For instance, term number 9 has only 45 dots associated with it. Not, for instance, both 45 and 50 dots. So there's only one number that is associated with each term. So 6 goes to 21, 7 goes to 28, 8 goes to 36, 9 goes to 45. We have a one-to-one relationship here. Okay. The sequence you explored in the activity is a sequence of triangular numbers. This sequence defines a function whose domain is, let's see what they say here, but it should be the set of, function whose domain is the set of all positive numbers, the set of all positive integers. Okay, so that means that it's a sequence because we're plugging in term number 1 and the first triangular number is 1, and we're plugging in 2 and the second triangular number is 3, etc. A notation for, I believe this is sequences, more common than f of x notation or function notation is to put the argument, which is the same thing as the input, in a subscript. So instead of raising it up, we lower it down. So this right here, the notation t sub 3 equals 6 is read t sub 3 equals 6. Okay, and by the way, this basically means that, this notation means that, let's see if I can get this to come alive, that 3 as an input is being sent to 6 as the output. So that's what t sub 3 equals 6 means, in the same way that f of 3 equals 6 would be function notation. So this is a function notation, this is a sequence notation, and if we wrote it as a coordinate pair, it would be 3, 6. So we have to read this friend right here as the input and this right here as the output. Okay? So t sub 4 and t sub 5, so going back to our table, I think we remember that t sub 4, that's the fourth triangular number, was 10. So we could say that t sub 4 equals 10, and t sub 5 was 10 plus 5, which was 15. So these are the points 4, 10, and 5, 15. So again, the notation here is different, but really it means t of 5 equals 15. This would be function notation if it was a continuous function and we can plug anything in. But if we can only plug in positive numbers, positive integers rather, whole numbers, then we write it in sequence notation like this. Okay. So why are explicit formulas important? So let's read what the book has to say about that. So it says, many sequences can be described by a rule called an explicit formula for the nth term of the sequence. Explicit formulas are important because they can be used to calculate any term in the sequence by substituting a particular value for n. So let's write that down. And let's say that explicit formulas are important because they can be used to calculate any term in the sequence by substituting a particular value for n. So remember, n is the input, we're plugging in n, and then we're getting out any term. So n is the term number, which would be 1, 2, 3, 4, 5. That's what we can plug into a sequence, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, etc. We can't plug in pi, that's not an integer. We can't plug in -2, that's a negative integer. Can't plug in 0. Actually, sometimes we can, but often we don't. And so we can only plug in 1, 2, 3, 4, 5. So the explicit formulas allows us to just plug in that number and get out a certain term. So for number 9, it says, quiz yourself, what is the 15th triangular number? Well, the first thing we need really is we need the explicit formula. And the explicit formula is on page 55, and it is T sub n is equal to n times n plus 1 divided by 2. So for any term number, we can just plug in the term number and get out the term. So we can plug in the 15th triangular number and get out what it is, or we can plug in 15. So that means T sub 15 should be 15 times 16 divided by 2, which is the same as 15 times 8, which should be 80 plus 40, or 120. To find T sub 100, that would be simply 100, we're plugging it in for n, times 101 divided by 2, which is the same as 50 times 101, which should be, let's see here, 5,000 plus 50, I think, or 5,050. My mental math isn't always the best, so let's double check that. 50 times 100 should be 5,000. And 50 times 1 is 50. So I do think that that is 5,050. So we basically just plugged in our number, our term number, and we got out what the term was. In the same way that if this had been written as f of x equals x times x plus 1 divided by 2, we could have said that f of 15 is equal to 15 times 16 divided by 2, which equals 120. And the point here is 15, 120. There's an input and there's an output. It's just that we're using a new notation because we are restricting our inputs to positive integers. Write P sub n equals 1/2 to the n using function notation. So this would simply be P of x is equal to 1/2 to the x. So you can see the difference there between sequence notation, which says P sub n. You should say that out loud. Maybe yell it and see if your cat freaks out. P sub n equals 1/2 to the nth power versus P of x equals 1/2 to the x. So just as an FYI, this graph would look like something like this. And this graph would look something like this. So when we see the 1/2 to the n, we would just have dots starting at 1. But if we see 1/2 to the x, actually this isn't quite right. It really should look like that. Okay, so there's a slight difference in this one being a connected continuous graph, this one, versus the sequence, which is just the dots. And I, made a few mistakes there, but it gives you the idea. Okay. Read through example 2. So example 2 is on page 56, and it says that it is common for people to save money in savings accounts, such as certificates of deposit, CDs, that yield a high interest rate paid once a year. Suppose you deposited $28,700. That's a lot of money that many of us maybe can't deposit. So I'll just make that known. And expected a 4.1% interest rate to be compounded annually. That basically means that you're just adding on the interest every year instead of all the time. Then the formula S sub n, so let's write this down. But I guess I'm gonna scroll all the way up here. The formula S sub n equals 28,700 times 1.041 to the n minus 1 gives your total savings at any time during the year leading up to the nth anniversary. Okay, so basically, let's see here. Total savings at any time during the year leading up to the nth anniversary. Okay, so I plug in n. N is the anniversary, how long it's been in there. And S sub n is the, what do I have? What is that again? Total savings in the year leading up to the nth anniversary. So compute the first 5 terms of the sequence. So S sub 1 would be 28,700 times 1.041 to the 1 minus 1. Well, 1 minus 1 is 0, so we have 28,700 times 1.041 to the 0. But anything raised to the 0 is 1, so that just means $28,700, which is basically saying that in the year leading up to the first anniversary of starting saving, I have $28,700, which makes sense because that's what I put in initially. Now S sub 2 is going to give me the amount in the account for that second year. So in the year leading up to the second anniversary. And that should be 28,700 times 1.041 to the n minus 1. So 2 minus 1, which is 28,700 times 1.041 to the 1. So I need to do 1.041 to the first power, which of course is just 1.041, and multiply it by 28,700, and I get 29,876 and 70 cents. So that is how much I have earned after the first year and how much is in my account, basically leading up to the second anniversary. Now S sub 3, I'm going to skip some steps. That should just be 28,700 times 1.041 to the 3 minus 1, which is 2. So I'm going to square that first. So 1.041, see if I can do this on my calculator. I'm going to raise that to the 2 and get 1 point, that doesn't make sense. Let's see here, I got to figure out how to do this. 1.041 times 1.041 is that, times 28,700 gives me 31,101.64. Then I could find S sub 4 and S sub 5. And what I'm noticing is that each time I'm just multiplying by 1.041 again. So if I multiply this by 1.041, I end up with 32,376.81. And if I multiply by 1.041 again, I get 33,704 and 26. So these are my inputs and outputs leading up to the first anniversary, second anniversary, third anniversary, fourth anniversary, and fifth anniversary, and how much money is in the savings account. Compute the 100th term of the sequence. Oh boy, well the 100th term of the sequence would simply be S sub 100 is equal to 28,700 times 1.041, all raised to the 99th power, because it's 100 minus 1. So 1.041, let's see if I can raise this to the 99th. X to the y, 99, is equal to, that seems a little big. Let's see if we can try that again. 1.041, then I'm going to raise it to the 99th power and get 53.4, wow, times 28,700, which is 1,532,865.74. So that basically means if you save this money at, 4% interest for 100 years, you're going to have a lot of money. And so it says, what does your answer to part B mean in the context of this problem? So basically what that means is if you save your money for 100 years, you will have $1,532,865. Wow, it's kind of a lot. Okay, let's see here. Let's scroll down here. Consider the increasing sequence 1, 3, 5, 7 of positive odd integers. Excuse me. 13 is the 7th term of the sequence. If this sequence is called D, what is D sub 11? Okay, make sure you're practicing saying D sub 11. You can even shout it and see what your parents do. Or siblings, or cats. D sub 11. Well, D sub 11 would be the 11th odd positive number. So let's see if we can figure out what that would be. Well, 1, 3, 5, 7, 9, 11, 13, 15. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 17, 19, 21. So D sub 11 is equal to 21. The 11th odd positive number is 21. So now perhaps the most important part, which is summarizing. So what is the relationship between sequences and functions? How do their graphs differ? Why do we need sequences? So a sequence is a type of function. Specifically, a sequence has only positive integers in its domain, like 1, 2, 3, 4, etc. So those are the only things you can plug in. Graphically, a sequence looks like a bunch of dots, but a function, we could even say continuous function, looks like a curve or line that is connected. We need sequences because it doesn't make sense to have fractional amounts of many things in the real world. So for instance, people don't really want to have half a person. Cars, you don't really have half cars. What else? I don't know. There's lots of things that you really don't want half of or a fraction of, and so it makes more sense to just have whole positive integers. What is the notation for sequences and how is this notation read? So basically the notation for sequences looks like A sub n equals something, some formula, and it is read A sub n or T sub n or S sub n. So that's the notation for sequences. Finally, in order to be a sequence, do both the domain and range have to be positive integers or just the domain? It is just the domain. So the range can be whatever you want it to be, but the domain must be only positive integers. So hopefully that makes sense. And I will see you soon, maybe, or maybe not. Okay, bye. Bye, 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 bye.